Okay, so good morning, everyone. Welcome back to Math 115. Today we're going to be moving forward. I'm not going to be going over the exam just because we still have a couple students that need to take the exam, so I'm going to write an alternate exam for them. I will maybe post a solution to the exam after I grade them, which, by the way, I'll probably grade the exams tomorrow and over the weekend. So I'd say expect to have your exam grades back by Monday at the latest, and maybe earlier than that. So that will be the exam. Your next homework is going to be over 1.4, which we started 1.4 already, but we haven't quite finished it. We're going to finish it today, and I'm going to assign the homework. And depending on how much of 1.5 we get through, I might also assign some of the 1.5 homework to be due on Sunday. Your next assessment is going to be Quiz 3, which is a week from today. It's on September 22nd. That's a Thursday of next week. And I'll let you know about the content probably on Monday. So other than that, I'll just remind you, my office hours are in person in LeConte 439 from 2:30 to 4 p.m. So that's where you can find me today, this afternoon, if you want to discuss anything. Also, the Tutoring Center, I have an update for you. I was wrong about the times. I had said previously that they're open Monday, Tuesday, Wednesday, Thursday from 10 a.m. to 3 p.m. They're actually open for an additional hour on these days. So it's 10 a.m. to 4 p.m. on Monday, Tuesday, Wednesday, Thursday. So make sure you make use of that awesome resource. You can go there and help get your homework done. Make sure you're 100%ing all the homeworks, study for your quiz, study for your exams. There are graduate students like me who can help you a lot. Any administrative questions before we start in on content for today? That's my plan, yeah. Is that okay?
Yeah.
It actually doesn't influence me. Actually, I've decided that that's not okay.
I mean, I can make it due Monday if you want, but then you might have another homework due like really shortly after that.
That will make no difference.
There's a homework due this Sunday. Do you want me to extend it to Monday? It's just going to sandwich it up against another homework, though. Do you want that?
4 days is adequate for like 20 problems.
All right.
4 days is completely adequate.
I mean, does the homework generally take you a long time? I feel like it's pretty short.
Yeah.
Okay.
Like some of the problems you're like, yeah, it's not even there.
Yeah.
Oh my god, that's
I love that.
favorite.
And the next one is like, ooh, he took it out.
My favorite after is like, please move on to the next problem.
And then you still get the green check mark. I'm like,
I'm like, Tom, my man.
thank you.
Yeah, I try to help you out just because I feel like I'm borrowing these assignments from another instructor, and I feel like some of them are just really, really repetitive, where they're like the homework where you had to find the slope like 10 times in a row. I was like, I removed like 8 of those problems or something, so I was like, that's just kind of absurd.
There's so much you can do.
All right. Well, I'm glad that the homework is manageable. I hope that it's helping you to learn. So let's start in on content for today, and let me start by reminding you what we learned last time. So last time we were starting, one more thing that I want to remind everybody of is that I'm, based on my inbox of my email, a lot of people in our class are getting sick, so just be aware that there's something going around. So if you feel sick, please don't come to class. Just watch the recording on YouTube, and then just complete the homework as normal. If you have a quiz and you feel sick, but you're like, I don't have a doctor's note, don't just come to class. Just stay home. We'll reschedule your quiz in some way, okay? So that's what I'd like you to do if you're feeling sick. second of all, it's starting to become the part of the semester where things start to get more stressful, I think. So please make sure that you're taking care of yourself. Please make sure you're taking care and curating your mental health as well. Get enough sleep, and avail yourself of all of the myriad of resources that we have at this campus in terms of mental health, such as the Counseling and Psychiatry Center, and also make sure you're curating your physical health, as I already discussed. So those are things that I just want to remind you of. And speaking of getting to harder parts of the semester, we started in on functions last time. So the reason that I say that things are going to be picking up a little bit is once we talk about functions, we're going to bring in these notions of like domain and range, and then we're going to talk about a bunch of different functions that are going to get progressively harder and harder. So we're going to talk about linear functions, quadratic functions, polynomials. We're also going to talk about rational functions, okay? So fractions of polynomials. And then we're also going to talk about transformations of functions, okay? So shifting them up and down and left and right and stretching and shrinking. And we're also going to talk about compositions of functions, okay? So plugging one function into another function. So this stuff is going to speed up relatively quickly in Chapter 1. And then I don't even remember what Chapter 2 is. We might even be moving on to trigonometry in Chapter 2. So I'm not trying to scare you, but I am going to tell you that the material from here on out is going to start to snowball a little bit more. So as long as you stay on top of it, I think you'll all be fine. But I just want to issue that advice. Okay, so a function we decided was from a set x to a set y was a rule that assigns to each element of x exactly one element of y. Okay, so the circumstance under which a relation does not qualify as a function is if we have something in the domain which is mapped to more than one output. More than one different output, I should say. Okay, so that's a big no-no for functions. So beyond that, we talked about the domain of the function, which is, of course, the set of all inputs that we can plug into the function. And the range was, of course, the set of all possible outputs. Okay, the set of all possible outputs. We talked about function notation and how to write down f of x, how to evaluate f of x. And we talked about different representations of functions. Okay, so sometimes we draw it like this, or we'll use a list of ordered pairs, or we'll use a table. And these work well when we have a finite set for our domain. By finite set, I mean there's only 4 numbers in this set, so it's a finite set, so it is a finite domain. As opposed to an infinite domain where, like, if the domain was real numbers or if the domain was 0, 1, right? There is an infinite amount of numbers in the set 0, 1, so that's an infinite domain. Okay, relation versus function. And then we talked about the graph. Okay, so how do we graph a function? Well, we just graph the ordered pairs x comma f of x. Okay, so we let the x value be whatever the x value is, and then the y value is whatever we get when we plug that x value into the function. Okay, so this is how we graph functions. And up until this point, we only talked about functions with a finite domain. So then we started talking about functions with an infinite domain, which are functions defined by equations. Okay, so unless you can write down like all of the relationships between a number and another number, which of course you can do if you have a finite domain, but if you have an infinite domain, what am I supposed to do? Well, you don't write down exactly what is the output for each number. You write down a rule which describes what the output will be based on a given input, right? So that's called the function rule. So for example, you could have f of x equals x squared. This tells us that the output of the function f gives you whatever you plug in, you square it, and that's the output. Okay, so you can think about a function as like a machine, okay? And so like if you've ever been to the airport, you know, you put your bag on the thing and then it goes through the x-ray and then some TSA member checks and sees if you have any liquids more than like 3 ounces, right? So this is kind of like that. We put the X in, and then the machine does some kind of gobbledygook, and then out comes our output, okay? All right, so that's functions, and to evaluate them, all you have to do is plug in, right? So if I want to find out what f of 2 is, all I'm going to do is I'm going to put 2 everywhere I see an x, except there's one special rule that I'm going to use every time I'm plugging into a function, and that is that I am going to PWP. I'm going to plug with parentheses, okay? The reason, can anyone tell me what is the reason that we always want to plug with parentheses? Sorry? Because of negatives, exactly. We have to be careful because if we don't plug with negative signs, it can get a little bit tricky to keep track of them. And if you're not careful, you can end up accidentally squaring a number that was supposed to be negative that wasn't actually negative, and then you end up with something that's not correct. So always, always, always plug with parentheses. It will serve you well, not just with numbers, but also later when we are going to do compositions of functions, when we are going to plug functions into other functions. Okay, functionception is what that is going to be called. All right, so domain of a function with a rule, we agree, okay, by we I mean someone else, agrees that the domain of the function is going to be the largest set of real numbers which result in real number outputs. Okay, so that's kind of vague. So we saw a specific example, which was this one. Where is it? There it is. Okay, so if we want to find the domain of a function like f of x equals 1 over 1 minus x squared, we just need to take the real numbers and exclude any numbers which make this expression unintelligible, okay? So by unintelligible, I mean not defined. So the numbers in this case were 1 and -1. So we took those away from the real numbers, and we call the domain all of the other numbers, which are okay to plug in, right? Okay, and then the range is, of course, given by the set of all possible outputs. So the way you do that is it's a little bit more abstract thinking, I think, to do the range, because you have to think about, okay, what is the domain and what type of function am I dealing with and what are all the possible outputs that I could get? Well, sometimes, in this case, we just looked at the graph and we saw, well, okay, from 3 to 5, x squared is an increasing function. So I know that the maximum is going to be obtained at the right endpoint, and the minimum is going to be obtained at the left endpoint, and everything in between is going to get hit. So the output of the range is going to be from 9 to 25. Since there's no way for me to get an output of, say, 4, right? Because to get an output of 4, the x value 2 would need to be in the domain, but 2 is not in this domain. So that's why 4 is not in the range. All right, so that was a lot. Any questions on what we did last time? All right, then let's talk about something else, which is the vertical line test. Okay, this is everyone's favorite thing to do when it comes to functions because it's really easy. So what is the vertical line test? Well, the vertical line test is a test which we can use to see if a graph represents a function as opposed to a relation. Okay, as opposed to a relation. Okay, so remember, what was the big difference between a function and a relation? What additional property does a relation need to have in order to qualify as a function?
There can't be two.
No repeating x values.
Yeah.
For the same
Yes.
y value.
No, yeah, so it's each x value needs to correspond to exactly one y value. So let me show you an example of two things which pass versus not pass the vertical line test, and I'll show you how to do it yourself. How would we graph the function f of x equals x squared, by the way? If I didn't know, if I had no clue that x squared was a parabola, okay, what would I do in order to graph it? I could plug in some points, right? So let's do that. I'll plug in 1 and 2 and 3 and -1 and -2 and -3. How about that? Okay, so for 1, I plug it in. What do I get when I do 1? I get 1 squared, which is 1. Okay, so that's why I go here. And then what do I get when I plug in 2? I plug it in for x. I get 2 squared, which is 4, right? So here's 4, maybe. And then 3 squared is 9, right? So it's up here. Okay, and then, of course, I'm going to go ahead and try plugging in negative numbers. So I'm going to do f of -1. And we all know that's just -1 squared. So I square 1, and it's -1, right? Or did I make a mistake there? What happened here? Did I do that correctly? No, why should it be 1? I'm confused. It's -1, I put in -1, I square it. I didn't put parentheses, did I? Right? I need to plug with parentheses. So let's see how it looks when I do that. Instead of -1 squared, I'm going to have -1 quantity squared, which is, of course, -1 times -1. If I multiply two negative numbers together, I get a positive number. So I get 1. Okay? So let's plug in. It's going to be 1, and then 4, and then 9, right? Okay, so if I were to graph this, I know 0 squared is 0. It looks like this parabola-looking thing. Okay, I didn't draw it very well, but you get the idea. Okay, so how do I do the vertical line test? All I do is I take my pencil. I hope you like my drawing, by the way. I take my pencil and I put it down on the paper and I slide it left and right. And what am I going to look for? I'm going to look to see if it intersects or touches the graph at two different spots, okay? And it doesn't. It touches it at one spot, one spot, one spot, one spot, one spot, all the way until I go over here. And like there's no part of the graph where my pencil is going to touch the graph at more than one spot. Okay, or my line is really what you're supposed to use, so not a pencil. So imagine this thing has infinitesimal width, right? All right, so let's see what doesn't pass the vertical line test. How about f of x equals the square root of x? If we assume that this is not the principal square root. So remember, the principal square root was just this branch of it. But if I do not the principal square root, I'm talking about, of course, the positive and the negative square root. So what would it look like? It would look something like this. Right? It looks something like that. Okay, so for example, where's 9? Here's 9, and the height of 9 is going to be both -3 and +3. Okay, because that's the square root of 9. Okay, so why is this a problem? Well, when I take my pencil here, what's going to happen? Oops. I touched the graph at 2 spots now. Okay, I touched the graph at 2 spots now, which is a problem because my function is supposed to be something that I can use in my factory. I should be able to plug something in and get something out, and it should be the same every time. But it's so confusing when I use my machine, and sometimes it's putting out 3, and sometimes it's putting out -3. I don't know what to do with that. So it's not useful. So this is why we take the principal square root. Okay, anytime we talk about f of x equals square root x, and we say that this is a function, or if the problem implies that this is a function, we're always talking about the principal square root, which the principal square root is defined to be, of course, just the positive side of this parabola, just the positive side. So this is the principal square root. All right, any questions on the vertical line test? I think that might be the easiest thing that you learn this entire year. What's harder to understand is why the vertical line test works. It's easy to remember. If it fails, it's not a function. But why? That's the question. Is why is it a problem if the vertical line test is failed? That's a deeper question. All right, any questions on that vertical line test? Okay, doesn't seem like it, so we'll move on. Okay, let's talk about finding the domain and range of a function just by looking at the graph. Okay, so here we have a function, which of course would be a piecewise function. Let's write down, by the way, what this function would be. Actually, I'm going to make it a little bit better looking here. I want it to go to, oops, not that one, this one. I want it to go to 2 here, like this. Okay, so let's write down what this function would be. It's a piecewise function. Okay, so what do I do when I have a piecewise function? I do one of these big brackets like so. And I'm going to define the rule of the function just based on the location in the domain. Okay, so, oh, no, don't delete that. I keep double tapping my Apple Pencil and it goes to the eraser. That screws me up every time. Okay, so how would we do this? Well, first I'm going to say this looks like part of the line y equals x, right? This part here looks like part of the line y equals x. So I'm going to say this is f of x is equal to x if the x value in the domain is in the interval from -1 up to 2. Right? From -1 to 2. And I'm going to put a bracket on from 1 to 2. So 1 up to 2, and I'm going to put a parenthesis on 2. Why do I put a parenthesis on 2 and a bracket on 1? Because I got a closed dot on 1 and an open dot on 2. Okay, so then how about the next part? What is the function value when x is between 2 and 3? So I'm going to say if x is between 2 and 3, and I'm going to put brackets on both, then what is the function value going to be? It's going to be 3, right? Because for every x value, it doesn't matter what x is. The value's always 3, right? So it's just a constant, okay? So constant functions look like horizontal lines, okay? Because you say, okay, what is the height of my function? It's always 3, right? That makes a horizontal line. Okay, so this is how we would write it down. Now let's talk about the domain. What should the domain be for this function here? It should be the set of all possible inputs. What do we think? Sorry? Okay, 1 to 2 are definitely numbers we can plug into this function. Can we plug in 2 to the function? We can. The value is 3 when we plug in 2, right? What about 2.5? Can I plug 2.5 into the function? Is that okay? Yeah, that's also okay. I've got a point up here. How about 3? Can I plug in 3? Yeah, I can plug in 3. So what is the set of all x values for which there is an output? It's from 1 to 3. I heard it somewhere out there. 1 to 3. Okay? Are we happy with that? Okay, so loosely speaking, I'm looking at this part of the x-axis, right? All the x values for which there is a point above it, right? That's what I'm looking for. All of the x values for which there is a point above it. Okay, how about the range? This one's going to be a little tricky. What are all of the y values which can be achieved by the function? All of the possible outputs of this function. So I heard 1 to 3. And let's forget about whether we're going to have brackets for a second. But can anyone tell me what's the problem with using an interval like 1, 3?
The numbers are between 2 and 3.
Yeah, we don't have any of these y values between 2 and 3, do we? So I think we should start with, let's start with this part, right? All these y values go from what? 1 up to 2, including or excluding 2? Excluding 2. So we go from 1 to 2, again with a bracket on the 1 and a parentheses on the 2. And then any other y values? I can also achieve the y value 3. If I plug in any of these numbers, I get 3. So how am I going to attach that to the range? I'm going to use a union. And now what should I write? I want a set which describes just a single number, the number 3. How do I write that? Well, that would be an interval, which would include 3.
Bracket 3, 3.
I want curly braces, or brackets, and then 3, and then a curly brace. Okay, so just like before, remember when we did the domain of like that other function, we had the curly bracket, and then we would list like 1, 2, 3, 4. Okay, so what I mean by these curly brackets is they denote a set of individual numbers, right? So I could also make a set which just has one number in it. I can have a bucket with just one thing in it. That's fine, right? So I'm going to do that by using these brackets like this, and I'm going to use the union to show that I'm going to take the set of numbers. I'm going to take a bucket, basically. And what numbers am I putting in the bucket? All the numbers between 1 and 2, including 1, not including 2. And also, just for added measure, I'm going to throw in 3. All right. Any questions on that part? All right, so you're starting to see probably why I was so insistent on you learning about this set theory stuff, right? Because this is going to be the language which we use to describe the domain and range of functions, which we're going to be doing constantly for at least for this chapter, actually for the whole rest of the class probably. All right, any questions on finding the domain and range from a graph? Okay, doesn't seem like it. So let's do some practice with a partner now, okay? So we got a lot of different topics to try here. So group up with a partner. We're going to take this function, which maybe I'll write it a little bit bigger, x squared plus 4x minus 5. So x squared minus, or was it plus 4x? It was plus 4x minus 5, right? Can everyone see that? X squared plus 4x minus 5. All right, and we're going to try to find out, is 2, 7 on the graph? Find all the values x such that x comma negative 8 is on the graph. We're going to find the y-intercepts, if any exist. Find the x-intercepts, if any exist. And then also list the domain and range of this function. Okay, so a lot of different things to talk about here with your partner. I'll be floating around and helping as needed. Hey, Jacob. Let's talk after class, okay? Thanks.
I think.
let's say the graph. If you put it like this, right, then you know that the graph, if we were to say this is equal to 0, right, then what would x be? -5 or 1, right? What does it mean if the function, if I plug in a number and I get 0? Then the height of the function is 0 when x is -5 or 1. So when x is 1, 2, 3, 4, -5, what's the height of the function going to be? Not 1, but 0. So we're going to put a point there. And then also, when x is 1, the height of the function is going to be 0 again. So that's how we get the x-intercepts. That's part D, right? But we actually don't need to graph this function to answer most of these questions. Right? We don't need to graph this function. What we need to do, if we want to find out is 2, 7 on the graph, then that means that what is true? X, comma, f of x equals 2, 7. This is what we want to check. This is the question. Is there an x value? If we plug in 2 for the x value, is the output f of x 7? So how would I check that? I would plug in 2 here and here and see, do I get 7 or not? See what I mean? And then for the second one, right, if I want to find all values x such that x, -8 is on the graph, then what am I trying to do? I'm trying to not plug in 8, but set this equal to 8. See what I mean?
It doesn't have to be.
Okay, it says we're supposed to find all values x such that x, comma, -8 is on the graph. So,
Oh, no, it's
if
okay.
we want to find the values x such that x, comma, -8 is on the graph, right? What am I trying to check? I'm trying to see, is there any number of x such that if I plug it into the function, then the output is -8, right?
So we plug 0 into
Is that good?
That's a weird.
No, that was like very early opportunity muscle.
No, because you read about all those.
Oh, wait, is that
Screech a muscle. I think we we just have
My girl was like, I was gonna go for like, she was like,
I don't think this is.
she was like, yeah, everything. So she's like, you're these really strong antibiotics, go to class today. Traumatized pain. Oh my god, it was just like, you're literally fine. You're literally fine. I was like, Emma. The hospital will do like everything. So they're doing like
We're looking for x.
test for
So,
I'm fine.
X's are negative Well, when y is negative 8.
Is there another entrance over there?
yeah. Seems like it. Yeah, well, it says one way though.
Such a
Why is it okay graph?
It's gonna be a one-way
Because if
class.
you go that way, you will, I was trying to come up with something creative.
I know the library, the stairs in the library mock for some like of the
Yeah,
floors.
you'll
that
get
didn't-
stuck and eaten by moths.
No, I actually got stuck.
Okay, so then it goes
Climb
nice.
upstairs.
I only just learned the other day that there's like 5 underground levels in the library.
I
You only just learned that?
That's
like.
I know, and I'm in my 4th year of grad school here.
That's something they say to orientation. Yeah.
There's 5 Well, because our library for such a big school looks so small.
Yeah,
So
it
we're
does.
just like, but I've genuinely been in it twice, and both times we're to get Starbucks. So,
No, I was in it.
Okay, how are we feeling? Are we about ready to talk about this as a class? Does anyone want a little bit more time to work? Okay, doesn't seem like it, so let's discuss. Okay, so let's address these one by one. So, someone help me. How am I going to check whether the point 2 comma 7 is on the graph of this function? Do I need to graph the whole function and see if that point is on there? No, silly. What should I do instead? I should plug 2 in, right? If I plug 2 in, then the height of the function is going to be given by whatever I get when I plug in 2, right? So if 2, 7 is on the graph, that's the same as saying that is f of 2 equal to 7, right? That's how you could rephrase that question. Is f of 2 equal to 7? So let's try it. If I plug in 2 with parentheses, I'm going to get 2 quantity squared plus 4 times 2 minus 5. So that's 4 plus 8 minus 5 is 12 minus 5, which is 7. So what do we think? I would say yes, it is on the graph. Okay, so I don't even need to draw the picture of the graph to see whether this point is on there, right? Okay, so that's really about the relationship between, okay, how do I think about a function and its graph? Like, what is the relationship there? Well, the graph literally represents what is the function output for a given input, right? All right, well, this next one is more challenging. How would I try to find all values x such that x comma negative 8 is on the graph? Such that, yeah, ST always means such that in math. Yeah, so what I'm trying to do is I'm trying to find an x value. I'm trying to find an x value such that if I plug it into the function, I get negative 8. I get negative 8 if I plug it into the function. So what am I trying to do? I'm trying to see, is there any f of x, which f of x is x squared how was it? Plus 4x minus 5? Plus 4x minus 5. Is there an x value that I can plug in that makes this equal to negative 8? And here's how we would solve it. Well, how would I solve it?
subtract the, add the 5.
Close. We're going to add the 8. We're going to get it all over to one side. X squared plus 4x, and then not minus 5, but plus 3, right, is equal to 0. Okay, this is, so you can just basically forget that this was ever here, right? If I gave you this question on the exam, you probably would have said, okay, it's a quadratic equation. I need to get everything to one side and then factor or something. So, okay, we move it over like that. Is there a way that this can factor? Yes, how can I factor it? Good. X plus 3 and x plus 1 is equal to 0. Now, what property is going to allow me to then set x plus 3 equals to 0 and also x plus 1 equals to 0, which I would then solve for x equals negative 3 and x equals negative 1. But why can I do that? Very good. The zero product property. I have two things being multiplied together and I get 0, right? So this is the first thing. This is the second thing. If I take two numbers and I multiply them together and get 0, then one of them had to be 0, right? That's what the zero product property says. also known as the ZPP by me.
Mr. Rocker.
Okay, so that's the zero product property. All right. How about y-intercepts? Who remembers how I find y-intercepts? Am I supposed to plug in 0 for x or plug in 0 for y when I'm doing y-intercepts? Supposed to plug in 0 for x. Okay, so if I do that, what do I get? I get f of 0 equals -5. So what is the y-intercept as a point, as an ordered pair? It's going to be what, comma, what? It's going to be 0, comma, -5, right? Because the 0 is the x value, and the -5 is the output, aka the y value. All right, what about x-intercepts? How do I figure out them? I plug 0 in for what? Y, which in this case is what? F of x, right? That's what I'm going to plug 0 for. So now I'm just going to solve what am I doing? X squared plus 4x minus 5 equals to 0. Okay, so now what do I do? I factor, right? X minus 5, no, plus 5, and then x minus 1 equals 0. So therefore x equals -5 or x equals 1. So what are my x-intercepts? They are -5, comma 0. Right? Because the x-intercepts are where the function touches the x-axis. If we're touching the x-axis, then the y value is supposed to be 0, right? Okay, so -5, 0, and also 1, comma 0. Okay, so y-intercepts have a 0 in the x spot. X-intercepts have a 0 in the y spot. So it's flip-flopped in that kind of weird way. It gets a little confusing. All right, now, how about the domain and range? I think this is by far the most complicated problem that we had. Was anybody able to find both the domain and the range? Anyone? Okay, how about just the domain? It is all real numbers. Okay, so let's see why. Okay, so this was our function. Let's find the domain and range. What did we say the domain was going to be when it's unspecified?
Largest set of real numbers that results in a real number output.
Exactly. Word for word. The largest set of real numbers which results in a real number output, right? So what are the things that are going to cause me to not have a real number as an output? There's basically two things that I need to worry about. What are they? Dividing by 0, and what else? There's something else, right? Even roots of negative numbers. Sully's hit the nail on the head. We can't do stuff like the square root of -1. Okay, those are what we also need to not allow. Do I have any square roots here? No. So am I worried about doing the square root of a negative number? No. Do I have any denominators here? So am I worried about dividing by 0? No. Domain is all real numbers.
Is the range -9 to infinity?
Let's check. So Griffin's guess is -9 to infinity. Well, I shouldn't say guess, but this is what he accomplished. Let's see if this is true. All right, well, first of all, I like that you have a plus infinity, right? Why do I like that? Because this is a parabola, and parabolas with a positive coefficient on the x squared term open what? Up or down? They open up, right? So we're definitely going to be able to go up to infinity, right, as our upper bound. There's going to be no upper bound, essentially. So we're going to have a lower bound. Where is the lower bound on a parabola? At the vertex. The vertex. That's where we're going to look for our minimum. So let's find the vertex. Well, there's two ways that you can do it. If you know the roots, I'll show you two ways. If you know the roots, which are, of course, the x-intercepts, which are, what, -5, 0, and 1, 0, then you can assume, okay, so this is 1, 0, and then we've got like 1, 2, 3, 4, 5. Here's 5, 0, right? If you have roots like this, then you know that the vertex is going to be smack dab in the middle of the roots. So one way that you could find the vertex is by saying, okay, well, right in the middle of this, it's like 1, 2, 3, 4, 5, 6, right? So if I want to be right in the middle, where am I going to be? I'm going to be at -2. That's also known as the average of -5 and 1, right? The average of -5 and 1, or right in the middle between them, the midpoint, if you will. Okay, so -2 is where I'm going to find the vertex. It's going to be like somewhere down here. But what is the height of that point going to be? What is the height of that point going to be? How do I find that? You plug in -2. Which, if I do that, I get -2 parentheses squared plus 4 times -2 and then -5, right? Is that the function? Okay, so it's 4 minus 8 minus 5, which I think is -9, right? Okay, so how do we feel about -9 to infinity? Should we include -9? Yes, because there is an x value, -2, namely, such that if I plug it into the function, I achieve -9. Okay, so this function looks something like this. Except more round at the bottom. Okay, so this is the point, -2, comma, -9. If you want to know, okay, if you want to know where the vertex is without doing all of this rigmarole, the vertex is always going to be at -b over 2a, comma, f of -b over 2a. Okay, so for example, for us, b was what? 4, right? And then a was 2. So -b over 2a for us was -4 over 2, which is -2. So that's how you get the x value of the vertex of a quadratic. All right, so I think that problem probably had something to challenge everyone. So first off, understanding the relationship between a function and its graph, finding intercepts, and also finding the domain and range in this more complicated setup where it's not specified, right? We have to take all the real numbers and then just throw out anything that makes our function blow up. All right. Any questions on this example that we did as a class? Yes.
When we write like domain and it's all real numbers, should it be like that simple, or is there like a way in point time that we should make negative infinity?
I mean, I think the easiest way is to write r, but you know what's the same as r is -infinity to infinity. Right? Is that what you were thinking? Yeah, you could write it like that if you want. Both are fine. But this letter looks kind of cool, don't you think? All right. Okay, let's talk about some different types of functions. So linear functions, what are they? Well, they're functions of the form f of x equals to ax plus b, where a and b are real numbers and a is not 0. Actually, a can be 0. That's fine. A and b are real numbers. Okay, so for example, f of x equals 2x minus 1. What does it look like? It's a function with slope 2x and y-intercept -1. So it looks something like that, right? So that's an example. All right, how about quadratic functions? Well, they look like f of x equals to ax squared plus bx plus c. And of course, a is not 0 for this one. And then a, b, c, and r. So a, b, and c are real numbers, and a is not 0. And we could just take the past one as an example. What was it? X squared minus plus 4x minus 5. So it had roots at -5 and 1. Oops. -5 and 1, right? So it looked something like that. Not a very good picture, but you get the point. It's a parabola. Okay, so those are quadratic functions. Polynomial functions look like f of x equals to, I'm going to do a weird symbol here, but you might as well learn it now because you're going to learn it later if you learn calculus. We're going to do a sum from n equals 0 to capital N of what? A n x to the n. A n x to the n. Okay, so what does this actually turn out to be? Well, I let n be 0, and then 1, and then 2, and then 3, and then 4, and then 5. Don't worry about the summation notation. But this is what it means to write a to the capital N times x to the capital N plus a to the capital N minus 1 times x to the capital N minus 1 plus dot 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 plus a 1x to the first power, which is just x. My laptop's really revving up here. And then plus a0, x to the 0. But x to the 0 is 1, so we just get a0. So what is a polynomial? It's a sum of power functions, right? In fact, why don't I say what a power function is? So first of all, let me give a better description of this in words. It is a sum of non-negative integer powers of x with real coefficients. Okay, so namely a1, comma, dot, 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 comma, an. Oh my god, I put an n in the wrong spot here. Sorry, this capital N minus 1 should be down below. It should be a subscript. It's not a power. Okay. A1 through an should be real numbers. Okay. And I guess if you want, an should not be 1. Or not be 0. Okay, so it's a sum of non-negative integer powers of x with real coefficients. That is what a polynomial is. Now let's talk about a power function. A power function is any function of the form f of x equals a x to the p, where a is not 0, and a and p are real numbers. So the difference between a power function and a polynomial is that some power functions are polynomials. Virtually no polynomials are power functions, as long as there are some. And what is the type of power function that is not a polynomial? It's something like f of x equals 3x to the 2/3, right? We can do that. So power functions don't necessarily have to have integer powers, okay? But polynomials always have integer powers, so nice whole numbers like 1, 2, 3, 4, 5, and so on. Power functions, we can do powers of 2/3. Am I running over time? No. I have plenty of time. All right. Any questions over these different types of functions? Those are gonna be our friends for the rest of the chapter, probably. Yes.
For polynomial functions, can you give like an example?
Sure, I could give an example of a polynomial function. Something like 4x to the 7 minus x to the 5th plus 3x to the 4th minus 21x squared plus 17. And in fact, why don't I make it 17.5? Just to illustrate that we can also have... It's okay for these numbers, the coefficients. They just need to be real numbers. They don't necessarily have to be... I can make this a 3/2 or something. The coefficients can be whatever they want. What needs to be an integer is the powers of x. See, 2, 4, 5, and 7. They're all positive integers. Okay, or non-negative integers, right? Because there's an x to the 0 here on 17.5. Okay, so that's an example of a polynomial. What's not allowed is something like x to the 2/3 or x to the -1. Okay, those are not polynomials. Does that help to clarify things? All right. I don't want anyone to worry about this summation notation. If you've seen it before, great. If not, well, hopefully this can be your first exposure to what that means, and I'm not going to test you on it ever. But you'll need to know it in calculus. So, I mean, you'll learn it in calculus. Any other questions on the difference between linear functions, quadratic functions, polynomial functions, and power functions? Yes, Griffin? Oh, you're good? Okay. All right. Then let's move on to a new section. We're going to talk a little bit about section 1.5. We're definitely not going to finish it, so I won't assign the 1.5 homework yet. But yeah, we're going to talk about now properties of functions. So far we talked about functions, how to graph them, how to identify them, how to evaluate them at a point, and also what is their domain and range. Now we are going to talk about the different types of functions that we have. Are you good, Emma? You drop your pencil? Is it down in front of you? Maybe Caroline can get it. Is it down there?
It's on the pizza.
Thanks, Caroline. Okay. So we're going to talk about the different types of functions that there are. Okay? That's what we're going to talk about now. And the first one is, okay, by the way, I don't, I mean, when I write like a wall of text like this, I don't expect you to write all of this down necessarily in class. I'm always going to post my notes onto Blackboard. So you can take out just like the relevant bits, and then also make sure that you get the idea of what I've written down here. Okay, so f is called increasing. So this is the first type of function we're going to learn is, hello? Did my Apple Pencil just die? I hope not. It shouldn't have, because it should have been charging this whole time. Well, that's strange, because it was plugged in. It says 91%. That seems like it should still be working. There we go. Okay. Wow, that was confusing. I bet you all thought you were going to get to leave early, didn't you?
I was like, that's it, we're done. No class.
Okay. Well, thankfully, or not thankfully, it's working now. So, increasing is the first type of function that we're going to learn about. So what does it mean if the function is increasing? What it means is that as we move from left to right, we are going up, okay? So here's an example of an increasing function. Here's another example of an increasing function, right? Things like this. So we're going uphill, basically, as we go from left to right. So f is called increasing on an interval, and it's very important that we specify on an interval, okay? Because some functions look like this, where maybe they're decreasing for a while and increasing for a while, and we want to describe the locations of x values where the function is increasing and where the function is decreasing. So the name that we use for this in mathematical language is that increasing and decreasing are local properties. By local, I mean just part of the domain. And if I say global, then I mean all of the domain. Okay, so that's the difference between local and global. So, f is increasing on an interval if what is true? For every two x values that I pick in that interval, with one being to the right of the other, what needs to be true? So one is to the right of the other. One needs to have that the height of the point on the left is smaller than the height of the point on the right. Okay, so let me show you an example of that. I did not leave myself nearly enough space to do this. I don't know what I was thinking when I wrote these notes. I'm going to move that down. Okay, so let's take a look at the function f of x equals x squared. Pretty easy to graph. It's just a parabola, right? In fact, why don't I even try to do this? Oh, yeah. That's nice. Okay. So we have a really cool looking parabola now. Great. So I want to describe the locations on the x values where the function is increasing, right? So the function is decreasing, 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 and decreasing, and then we hit 0, right? And then the function starts to go up, right? So I think about, imagine myself if I was walking, right? If I'm walking on this surface to the right, am I going downhill or am I going uphill? Okay, if I'm going downhill, then I'm decreasing, okay, d and d. If I'm going uphill, then I'm increasing, okay? So, I want to describe the locations A and B such that if the x values are between A and B, then I'm increasing. Okay, so in this case, it's going to be from 0 to, actually I'm going to use a parentheses here, 0 to infinity. Okay, increasing on 0 to infinity. Why? Because if I take any x1, which is to the left of another x2, two x values, one of which is smaller than the other, then what is true? This is f of x1, and this is f of x2. Then what is true? If x1 less than x2, then f of x1 has what relationship with f of x2? What goes in the middle here? Yeah, f of x2 should be larger than f of x1, right? So what is that really saying? It's saying if I go to the right, I also go up. That's what this says. If I go to the right, I also go up. Okay? And this works for any x1 and x2 which are between a and b, which in this case a is 0 and b is infinity. Okay? So this function, x squared, is increasing on the positive half of the x-axis, also known as 0, infinity. Any questions on that? Okay, it's okay if you do have questions, because this is a little bit difficult to grasp the first time you try it. Let's try another one. We'll talk about decreasing now. Oops, I added the page in the wrong spot. Let's move you up there. Okay, let's talk about decreasing. Okay, so what's going to be decreasing? Well, f is called decreasing on AB if for every x1 to the left of x2, we have what? The opposite should be true, right? The point on the right should be lower than the point on the left. Okay? So let's talk about x squared again. Let's take a look. Do another one of these. Okay, so what do I want to be true? So first of all, it's going to be from negative infinity up to 0. I think we know that's, generally speaking, where this function is decreasing. But let's talk about why the math makes sense. So here's x1. Of course, we still have x2 to the right of x1. And what should be true? Here we have f of x2. And up here we have f of x1. So what needs to be true? If x1 is to the left of x2, then the point on the right needs to have what relationship to the point on the left? It needs to be, well, I think I said it in a weird way. Which one do we need to be bigger? We want x1 to be larger in this case because we're decreasing. Okay, so it's weird because now we're switching the signs. If x2 is to the left of x1, sorry, I said that backwards. If x1 is to the left of x2, okay, like so, then the point on the right side needs to be lower in order for us to call ourselves decreasing. All right? Any questions on that? So the only difference between increasing and decreasing is this sign should be flipped, right? Just want to think, am I going downhill or am I going uphill? If I'm going uphill, then my elevation later should be bigger. If I'm going downhill, then my elevation later should be lower, right? All right, now let's talk about what happened. Whoa. What happened here? Oh, I understand. Wow, okay, that's confusing. I think this came from, not there, but this came from here, somehow. Okay,
Right.
that was confusing. I guess because it's drawn kind of over the half of the page. I think there's a page gap there. Okay, whatever. It's not gonna phase us. Okay, f is called constant. That's the other option, right? We're either going uphill or downhill, or we're not going uphill or downhill. So f is called constant on an interval if for every x value between a and b, we have that the height of the x value on the left is the same as the height of the x value on the right. So let's talk about f of x equals x squared. Are there any intervals on which f of x equals x squared is not changing? Any intervals? No. There's no intervals on which it's not changing. It's either going downhill or it's going uphill, or we're at 0, right? But 0 is not an interval. It's a point. Okay, so there's no collection of x values such that if my x value is smaller than the upper bound and bigger than the lower bound, then I'm constant. So what would I say for f of x equals x squared is constant on, I want to describe the set of numbers which we are constant at. How do I describe the set which doesn't have any numbers in it? I could do 2 squiggles, and then there's another symbol I could also use. Yeah, it's a circle with a cross through it, like that. So this is called the empty set. Okay, we call it empty because it's like a bucket that doesn't have anything in it. Okay. It's like that show. What is it called? The Fairly Odd Parents. Did you ever see that show? You remember the episode where Timmy's dad is saying something like, "This is where I would put my trophy, if I had one," right? Yeah, it's kind of like that. I have a bucket, and I'm going to put inside my bucket all the places where the function's constant, but I don't have any of those, so it's just an empty bucket, right? Okay, so let's talk about this picture here. This is a more instructive example. Let's find the interval on which this function is constant. Well, the interval on which this function is constant is pretty easy to see, right? It's this part, yeah? So what are the x values that correspond? It's from 2 to 5. So we're constant on 2, 5, and we are increasing. Where are we increasing? Negative infinity up to 2, union 5 to infinity, right? Okay, so that's where we're increasing. So I just want to remind everyone that these are local properties, okay? Meaning that they are only in effect in a given subregion of the domain, okay? Unless you have a function which is linear, in which case you could say that the function y equals x, for example, is increasing globally. Okay, that's it for today. Have a nice weekend.